So, good afternoon, everyone. I hope the first day of the first EMEA OCP Summit has been as fruitful for you as it has been for me. We had a lot of good talks with some existing customers, but also with some potential new customers. My name is Kristian Vättö. I'm responsible for SSD products here in EMEA for Samsung Semiconductor. And I'm basically here today talking about storage. Actually, Facebook gave a very good introduction to my topic because what I'm doing here today is talking about disaggregated storage and basically the key technologies that are driving this fundamental change in the computing architecture. So starting with a bit of a background, if we look at the growth of data versus the storage media density over the past 7 years, we can see that there's a massive gap between these two. So basically, the amount of data grew about 6 times faster than the density of HDD or SSD. And this is already taking into account that today we're shipping a 32 terabyte, 2.5 in SAS SSD, but even that is not enough to keep up with the data growth. And naturally, as we enter to the next 7 to 8 years with new applications such as 5G, IoT, and autonomous driving, this gap is only going to increase because these new applications are more data intensive and are collecting more data than what we have today. So obviously, what the IT industry needs is 3 very basic things, which are, of course, ultra-low latency. So if we talk about, for example, 5G and autonomous driving, these are designed to operate at sub-millisecond latencies. So not only the network needs to support this, but also the underlying storage architecture needs to have the inherent capability of supporting very low latencies to actually drive these new applications. On top of this, of course, there will be a need for a higher throughput, for more performance and speed, because especially with IoT, there will be billions of devices connected, billions of sensors collecting data. So we need interfaces that are capable of actually transmitting that data between the hosts, between the different systems to the actual drives to themselves. And of course, since we are collecting and storing more and more data, the actual standards need to be able to store more and more data per space. So we need more higher density storage because otherwise the only option to actually grow is just to increase the space. But the problem today in storage infrastructure is that it's relying on obsolete standards. So starting with the actual hard disk form factors, 3.5 inch and 2.5 inch were both introduced to the market before NAND flash was even invented. So it's clear that these 2 form factors are not ideal when we consider today's applications, today's capacity requirements, and of course the underlying technology, which will be more and more flash-driven as we go forward. And on top of that, the existing interfaces were also designed and introduced more than a decade ago, so SATA and SAS. And by the time these standards were being designed, SSDs were not mainstream technology. SSDs were still a very small niche for some kind of special workloads, so they were not widely adopted in the industry. So these specifications were actually not designed for SSDs in any way. They were designed for rotating media and their characteristics, be it the latency, capacity, throughput, all these different parameters. So my talk here today will be centered around 2 new technologies. The first one being NVMe, the new drive protocol on the SSDs, and more importantly, NVMeoF fabrics, which then extends this new protocol over a fabric, over a storage fabric to make it remotely accessible. And on top of this, we also have a new SSD form factor called NF1, which is packing in more density than any existing form factor to date. So to kick things off with NVMe, now I could be standing up here talking about I/O scheduling and different polls and all the other nitty-gritty details of NVMe, but I suppose most of you are not storage engineers who are actually developing these things. So I prefer to give more of, let's say, a real-world example. I guess most of us are commuting to an office on a daily basis, so we know how bad the traffic gets, how bad the traffic can be in the morning. So just imagine that SATA and SAS are single-lane roads, which they actually are, because there's only a single queue available, a single queue going to these drives. So what it means in storage environment is that basically all the applications, all the different users are cramming into that one lane of traffic. So now again, if you think about your morning commute, there will be no traffic problem if you were the only one driving there. But since you have a lot of other commuters, a lot of other users in today's cloud infrastructure, the SATA and SAS interfaces are not capable of supporting multi-tenant workloads that are dominant in today's cloud infrastructures. Whereas if we take a look at NVMe, it's basically abolishing all these bottlenecks because it supports more than 65,000 I/O queues. So basically, every application, every user can have its own I/O queue, meaning that it will not be impacted by the other users of that drive or the other users of that service. On top of that, as SATA and SAS were designed for HDDs, they were never meant to be scaled for high throughput bandwidth because rotating media, pretty much, you can barely get 5 gigabits of bandwidth out of a drive. Whereas in case of NAND and SSDs, we are able to support tens of gigabits per bandwidth per drive, coming from the inherent benefits of non-volatile memory. So basically today, NVMe is using PCI Express. Most of the mainstream drives shipping today are Gen 3x4, meaning up to 32 gigabits of bandwidth. But over the next 18 months, there will also be Gen 4 available, effectively doubling the available bandwidth to the SSDs. And this is basically removing the speed limit. So this is like driving on a German Autobahn from now on. And if we move up to the stack, more to the NVMeoF fabrics of the side, what NVMeoF fabrics does, it allows the same NVMe protocol to run over a storage fabric. So basically that means all the way from the application, even if the application is sitting on a separate compute node, the traffic between the application and the drive will all be NVMe, end-to-end NVMe. Whereas today, if you were to implement an NVMe solution without NVMeoF fabrics, if you want to transfer that I/O over a network, the only option is to actually translate that into a SCSI format. And naturally, since SCSI was designed, or it's a very obsolete and ancient technology in the first place, you're basically killing all the latency benefits that NVMe is bringing to the table. So the only way to make a scalable, high-performance NVMe solution is to use NVMeoF fabrics to enable an end-to-end NVMe connection. And another key technology that is driving NVMeoF fabrics is RDMA, short for Remote Direct Memory Access. Because what it allows is that the application can actually bypass the host CPU and kernel layers and thus access the storage or the NVMe storage using the NIC itself. So this does not only improve the latency, but also it frees up the whole CPU cycles for the actual application. And ultimately, that's what all the workloads want, because then you can use the CPU cycles to actually process the data, to analyze the data, rather than just using it to actually transfer the data to the host system. So moving up the stack to the actual storage architectures. So today, there are pretty much 3 key technologies in the industry: direct attached storage, storage area network, and network attached storage. These are all pretty standard, pretty old technologies. And of course, they all have their benefits, but also their limitations. So for example, DAS, it tends to be a very cost-efficient solution, but because it's only connected to a single host, it's very limited in terms of scalability, because you cannot add as much storage as you want, and the storage is not disaggregated. So in case you want to actually increase the amount of storage, you also need to improve or increase the amount of compute nodes. And on SAN side, while this is still a very dominant technology, especially in enterprise storage, it's a very old and very expensive and complex technology to manage, because basically you have a different fabric for the storage network using fiber channel, and then you would have a different network using Ethernet to actually connect the different host systems together. So again, this is not a scalable solution in a hyperscale or any high-density data center environment. And last but not least, network-attached storage itself is fairly scalable, but because of the limitations of TCP, it tends to have a quite limited performance. So now, the benefit of NVMe is that it's actually architecture independent. So it can be in any of these architectures that I outlined here by simply attaching to existing networks, because NVMeoF fabric supports, it can run over Ethernet, InfiniBand, even fiber channels. So it works with any existing network. But actually, the biggest innovation in NVMeoF fabrics will be happening inside the storage server. Because if we take a look at a traditional or conventional NVMeoF fabrics array, and this could actually be a normal SCSI array or whatever storage array that is sold on the market, a lot of the components that go inside these solutions are actually not storage. They are just there to enable that storage to be remotely accessible. So if we take a look at what's inside, normally you would find dual CPUs, in case of NVMe, a couple of PCIe switches, and 200 gig Ethernets. But what Mellanox Bluefield SoC will enable is actually, it will integrate all these functions in a single SoC. So it has 200 gigs of Ethernet or InfiniBand connectivity, together with 32 PCIe Gen 4 lanes, accompanied by 16 ARM cores to actually manage the functions that the CPU would normally do. So what this actually allows is to build a JBOF kind of architecture, but with all the traditional storage array features. So what this means is NVMe fabric storage will actually be much more cost efficient in the long term than what you can find today in normal all-flash array or other storage array type of solutions. So moving on to the actual drive form factors themselves. So as I mentioned earlier, the 2.5-inch, okay, my PowerPoint just crashed. Okay, so as I mentioned earlier, the 2.5-inch form factor was introduced 30 years ago, and that was way before the time SSDs became mainstream. So actually, the only reason the industry started using 2.5-inch for SSDs was the fact that it was compatible with the existing HDD infrastructure. So this made it very easy for basically any HDD to be replaced with an SSD without any change in the storage architecture. But because this was not optimized for SSDs in the beginning, 2.5-inch cannot offer the sufficient storage density or thermal envelope to actually support high-performance, high-density SSDs. So the first step the industry did was introduce M.2 about 5-6 years ago. But this was actually driven by the PC industry. So the PC vendors wanted to introduce their ultrabooks, their ultra-thin PC notebooks. So they needed something that's much thinner than a 2.5-inch. So the industry then decided, okay, let's develop M.2 spec to fit into that criteria. But because it was designed mainly for the PCs, it didn't have the enterprise features that we need, such as dual port or hot plug or front loadability. And also, the form factor, the physical size of the drive was not optimized for SSD or for high density. So it could not hold enough capacity to actually be a viable solution for all-flash array type of installations. So recently, there's been a new form factor, or actually a bunch of form factors called EDSFF, which are basically improving the storage density by optimizing the form factor for SSD media. But from Samsung's point of view, EDSFF is not the right solution because it's actually 3 different form factors. So you have on top there, you have the EDSFF 3-inch. In the middle, you have the EDSFF 1U short, and then, of course, the 1U long on the bottom. And on top of these all support 2 different thicknesses and also 3 different connectors. So what you actually end up with is 3 different form factors, actually 15 different form factors, meaning 15 different designs, server designs, also 15 different part numbers for us to produce. So 15 times the complexity that we've had so far in the industry. And on top of that, even though I'm standing up here talking about how NVMe is the future, there is still a huge market for the legacy interfaces being SATA and SAS. So these interfaces are not going anywhere in the next 5 years, maybe in 10 years, who knows. But definitely there is still a market for these drives. So Samsung's solution is a form factor called NF1. This basically takes the concept of M.2, but applies the missing features. So we made the actual physical spec slightly wider than the M.2, which gives us enough room to fit in 2 rows of NAND packages. So we can actually fit in twice the capacity compared to an M.2, which today yields up to 16 terabytes, and in the near future up to 32 terabytes as we apply QLC to this kind of form factor. And we support all 3 interfaces, those being PCIe, SAS, and SATA. And with a 16-watt power envelope, we are also ready for PCIe Gen 4. So the drive we have today is Gen 3 based, up to 10 watts. So we still have enough headroom to actually support PCIe Gen 4 when it comes around next year. And of course, this is supporting dual port for still mission-critical applications, and also hot plug and front loading for easy serviceability in a data center environment. So we actually think this is a perfect spec for OCP because it fits into all the 4 tenets that OCP is using as its foundation. So starting with efficiency, by being able to fit in more capacity, not only on a single SSD, but also on a single server, single use server, single rack, we can minimize the space taken by storage, and also reduce the power consumption by requiring less cooling, requiring less actually compute nodes and other systems, other components running on top of the SSD. And by being all in one spec, so not having different lengths, different thicknesses, or other specs, we think the all-in-one approach makes this more efficient because basically it's only one spec for any of your servers, any of your designs. And on top of that, especially from my point of view, since I'm also working on the commercial side, just having one part number is much easier than having 20 different part numbers, meaning it's also much easier for you as customers to use this spec, find it widely available on the market. So on the scale side, as I mentioned, this pack is supporting both front loading and also LED indicators. So this makes it very easy to service in a data center environment, just like any existing storage form factor today. And this is actually already an approved JEDEC standard. So this is a fully open spec. It will be published early next year on the JEDEC forum. And also basically any JEDEC member can also contribute to this spec in the future. And ultimately, in terms of impact, by driving lower TCO with higher density, with less power, it's beneficial for any kind of data center usage because it's providing much better total cost of ownership. So of course, that's just a simple form factor, but we've also co-worked with AIC to develop a solution around it. So the solution is called Mission Peak. It's a one-use system supporting up to 36 of these NF1 drives, and with each drive supporting up to 16 terabytes, we can have a usable density of more than 550 terabytes in a one-U system. So for comparison, the best you can do today with a 2U 24-drive system is roughly 380 terabytes. So this is much more than you can fit into a 2U system today using existing form factors. And not only density, but because this is NVMe storage, we can enable much higher performance than any of the legacy architectures around. So if we talk about local performance without any networking involved, we can enable up to 10 million IOPS from this 1U box. And when we go over a fabric using NVMeoF fabrics, we can enable nearly the same direct attached storage performance because of the inherent benefits and scalability of the NVMeoF fabric spec. So we actually thought hard, how can we actually bring this solution to the market? Because we are just making the drives. We are not making the solution, the software, and everything else that goes in. So we decided to partner with some other companies like Mellanox, ASC, and E8 Storage to actually develop a turnkey solution. And not only that, we then decided that why don't we make this easy for everyone to test? So we came up with this POC as a service concept. So what we did was we actually installed a fully functional system to a co-location data center called eShelter. So they are one of the market leaders for co-location in Germany. And they have this service called Innovation Lab, where basically any vendor can come in and install their latest and greatest stuff, and then give remote access to any possible customer that wants to test it. So this system has been up and running there since Friday. We have a live demo of this on our booth, so it's fully functional using the E8 storage software. And basically, the benefit of this kind of POC as a service approach is that it significantly reduces the time for you to do a POC. Because we've already done everything. We've installed the system, we've tested the system, we've installed all software, all updates, all that's necessary to actually enable a POC. So from your point of view, if you want to test this, all you need from us is a login, and you can log in remotely and run whatever application, whatever workload, file system, whatever on the server, because everything there is already installed. Whereas in a normal type of POC, I guess most of us are familiar with, there's a lot of pain points to actually enable it. First, you need to justify why should I spend this amount of money and this amount of resources to actually build the system, whereas in this case, you don't need to invest anything. This is completely free. All you need to do is log in and run some tests. So I would like to urge you all to actually come to our booth, to actually see the live demo. So it's up and running in the eShelter data center. We are VNCing to the system so we can actually see everything that's going on. We can do up to 3 million IOPS with this thing currently without any optimizations. And naturally, what I would like to see is as many of you as possible to actually sign up to test this thing, because we can start tomorrow. The system is there. It's ready for anyone to test. So I hope to see as many of you as possible. We are at 8:22. We're almost next to the registration. And that's basically concluding my part. So I hope you all have a good afternoon. Have some nice drinks in the networking session, and I hope I speak to many of you.